This is lesson 21 of the quantum mechanics, a mini lecture series titled Wave Particle Duality, part 1. So we have the idea that light is made of particles, according to Einstein. Light is made of particles. And even Newton proposed this in 1704. And Einstein believed that there was to be something new, a new explanation to come that can allow for a duality. Okay, duality means the merging of two different ideas. Duality of the particle wave behavior of light. So Einstein genuinely believed that there should be a theory, an upcoming theory, which can describe light as being made up of particles and waves. And the answer came in 1924 by the French physicist and prince Louis de Broglie in Paris. He introduced the idea that particles may exhibit wave properties. So a particle may be described by a wave. Point-like object, described like that. And he wrote that perhaps the wave-particle duality, as it was known, as he called it, wave-particle duality, can be generalized and applies to everything that we see in the universe, every physical object. And he believed that a wave accompanied the particle through its motion in space and time. Suppose you have an electron here. You draw it like this, actually. An electron. It was pictured that it perhaps has an associated wave with it. Okay, these were called pilot waves in de Broglie's terms, which guide the particle in its motion. Now, it was very simple maths that de Broglie developed. His theory started off with Einstein's E equals mc squared. E stands for energy, measured in joules. M stands for mass in kilograms, and C is just a number. It's the speed of light, 3 times 10 to the 8 meters per second, or 300 million meters per second, in other words. He started off with this, and you can rewrite this as just mc times c, right? Because squared means take that thing, the c, multiply it by itself, if you remember. Now, since mc is just mass times speed, that's also the momentum, okay, p, of a photon. In this case, we're dealing with light. So therefore, E is just p times c. All right, momentum is mass times velocity. And that's equal to p f lambda. If you recall, from v equals f lambda, we're just now using c instead of v because we're dealing with light. Get this. Right, now setting E equals hf, okay, from the Planck-Einstein relation to this expression, hf, because E equals mc squared and E equals hf, they're both measures of energy. So hf is equal to p f lambda from here. And rearranging, let's rearrange. Let's take the f over, divide both sides by f, f cancels out. You will get lambda. So h equals p lambda. So therefore, lambda is just h over p. These three dots mean therefore. So in other words, as the wavelength of light increases, the momentum of the light wave decreases. This equation here, lambda equals h over, let's put it like this, mc. Lambda is a wave property. M is a property of a particle. So this is called de Broglie's wave-particle duality. Okay, if you were to plot it, it would look like something like this: lambda, wavelength, momentum. You get an inverse relationship. This is an inverse relationship. Okay, if you increase wavelength, you decrease the mass, vice versa. Or I should say, if you increase the wavelength, okay, of a wave, you decrease the momentum, and vice versa. Okay, for electrons, you would use P equals mv instead of P equals mc. Okay, so now the electron is a particle, is a wave, as opposed to being a particle, as Thomson proposed in 1897 when he discovered the electron. This was a great result de Broglie produced in his doctoral thesis, his PhD thesis in 1924. That now a particle can be described as a wave, okay, because equation's got lambda. Okay, and p is momentum. It's a measurable property of a particle.